All right, so let's take a look at what's going on with this first problem. So we have that the particle moves along the line so that its position at any time t is greater than or equal to 0 is given by our function s of t equals t squared minus 4t plus 3. S is measured in meters and t is measured in seconds. So when we're asking what is the displacement of the particle during the first 2 seconds, we're asking what is its position after 2 seconds minus its position at the beginning. So when s is equal to 0, or t is equal to 0, we're going to have just that its initial position was 3, because t squared and negative 4t both evaluate to 0, and we end up with just 3. And then when t is equal to 2, we get 2 squared minus 4 times 2 plus 3 is going to give us a position at that point of 4 minus 8, negative 4, plus 3 is negative 1. So its displacement during the first 2 seconds is going to be then negative 1 minus 3, and that's going to give us a displacement of negative 4. And basically it's because it moved from a position of 3 to a position of negative 1. So it moved 4 units to the, on our number line, 4 units to the left. Okay, the average velocity over the first 4 seconds, so that means we want to figure out its displacement over the first 4 seconds and divide that by 4. So we're going to plug 4 in for t, and we're going to get that s of t is equal to 4 squared minus 4 times 4 plus 3, and that means that we get a value there of 3. And so its displacement over the first 4 seconds, it went from a position of 3 when t was equal to 0 to a position of 3 when t was equal to 4, which means its average velocity of the particle over the first 4 seconds is just 3 minus 3 over 4, and that just gives us an average velocity of 0, and that would be in meters per second. Okay, now when it's asking for the instantaneous velocity, now we're talking about the derivative. And so the derivative of t squared minus 4t plus 3 by the power rule is going to give us 2t minus 4, and so that's s prime of t. And when we plug in t is equal to 4, we're going to get 2 times 4 minus 4 is going to be equal to 4 meters per second as our instantaneous velocity at time t is equal to 4. The acceleration, we know we can compute by finding the second derivative, or in other words, the derivative of 2t minus 4. And the derivative of 2t minus 4 is just 2, so the acceleration when t is equal to 4, and actually at every other time, is just 2. Okay. So now we're taking a look at the graphs of both s of t and s prime of t. So we have here, this red one is our position graph, and our velocity graph is this line here. And a couple things that we can see. First of all, we can see that from t is equal to 0, when our position was 3, down to t is equal to about 2 here, our particle is traveling in a negative direction, and then it starts to travel in a positive direction from this point up until our end point here. This is also reflected in our velocity, because along this portion of the derivative curve, our slope, or rather the value, is negative, which means that the slope of our original function is negative, and it also means our velocity is negative, whereas up here we get a positive velocity. Where this particle is at rest is this one instant right here, when the velocity is equal to 0, and we'll also see that the tangent line for our position function has a slope of 0. So for that instant, its velocity is neither positive nor negative. Okay, let's continue on here. Go on to the next page. Okay, so now we take a look at this problem where we have the number of gallons of water in tank T minutes after the tank has started to drain is given by this function Q of T is equal to 200 times 30 minus T, that quantity squared. Okay, how fast is the water running out at the end of 10 minutes? So this is asking us for the rate of change of the water in the tank at a particular instant. So that means we need to find the derivative of Q of T. And Q of T, we also know, is equal to 200 times, this thing expanded gives us 900 minus 60T plus T squared. And so what we're going to end up with for a derivative is 200 times negative 60 plus 2T. And if we now plug 10 minutes into that, we're going to get 200 times negative 60 plus 2 times 10 is going to give us 200 times negative 60 plus 20, or negative 40. And that's going to give us a rate of negative 8,000. And we're told that it's going to be in gallons per minute. Okay, the average rate of change at which the water flows out during the first 10 minutes requires us to figure out how much water is in the tank at the beginning, when T is equal to 0, and when T is equal to 10. So when T is equal to 0, we end up with 200 times 30 minus 0 squared, or just 200 times 900, which is going to give us 180,000. And then at T is equal to 10, we're going to get 200 times 30 minus 10 squared, which is going to give us 200 times 20 squared, or 200 times 400, which is going to give us 80,000. And so the change in the water in the tank over the first 10 minutes, we go from 180,000 to 80,000, so we get 100,000. And that's negative because we went from a higher to a lower quantity. So really what we did is we subtracted 80,000 minus 180,000 over 10, and that's going to give us a rate of negative 10,000 gallons per minute on average for the first 10 minutes. Okay, next question here. This shows us the velocity of a particle moving on a coordinate line. And just for reference, by speed, we mean the absolute value of velocity. So here in our graph, we can see that the velocity is negative between 1 and somewhere between 4 and 5. And that means that if we were measuring the speed of the particle instead of the velocity, we would have to take the absolute value of this portion, which would mean basically we would flip it up like this. Okay, but when is the particle moving forward? When is it moving backward? It's moving forward whenever its velocity is positive, and so that is right here, here, and here. And so from 0 to 1, and then say from about 4.7 to 7, something like that. When it's moving backwards, then would be the rest of that interval, or not actually, it would be from 1 to about 4.7, so it would be the rest. Okay, so when is the particle's acceleration positive? Its acceleration is positive when the velocity is increasing, and so that would be from this point here up to this point here, when we have a positive slope on the velocity graph. So from t is equal to 2 to t is equal to 6. And so it's negative on these other intervals from, so negative from 0 to 2, and then also from 6 to about 7. Okay, its acceleration is 0 when we just are at these points, like right down here and right here, when we're changing from a negative to a positive acceleration. Okay, so when is the particle moving in a positive direction and speeding up? So it's moving in a positive direction, as we said, whenever its slope is, whenever the velocity is positive. And for it to be speeding up, its acceleration also has to be positive. So the only time when that is happening is between around 4.7 and 6 seconds. And that's, we can tell by looking at the graph and seeing, okay, the acceleration is positive and we're moving in a positive direction here because we have a positive velocity. It's above the x-axis in the velocity curve. Okay, when is the particle moving in a negative direction with speed decreasing? Okay, so it's moving in a negative direction whenever the slope is negative here, which is whenever the velocity graph is below the x-axis. And its speed is decreasing when the speed is moving closer to 0. So the absolute value of the speed is going down, and that would be along this interval right here from 2 to about 4.7. And so again, over that interval, our velocity is negative, as we can tell because the velocity is below the x-axis, that portion of the velocity curve, and our velocity is going closer and closer to 0 over that interval. So our speed is decreasing. Okay, and that is it.